In the next 30 minutes, I'd like to talk about how Target built a distributed architecture for managing real-time inventory, right, across all the items that we sell on our digital platform, right? Target has a pretty strong digital presence across our native apps, mobile web, and also our target.com. So we'll talk through the architecture that's scaled to over 1 million requests per second with a response time of under 10 milliseconds, right? So we'll talk through the complexity of the problem. We'll also talk through some of the architectural principles. We'll switch focus to some of the design goals, and we'll also discuss some of the lessons learned in this journey, right? So that if you were to develop a distributed architecture with a similar scale, you can have some ideas on how to approach it, right? So before I deep dive into the solution, I want to spend a minute on why is inventory have to be real time, right, in an e-commerce side, and what happens if inventory is not real time, right? So what you see in front of you is a fairly standard product details page, right? The kind of page that we all run into every day in our lives, buying favorite items from our favorite online retailers. If you take a closer look at this page, right, there is item information, there is content here, there is price information, there are offers, ratings, reviews, but you also see the inventory information here, right? A lot of the data that you see on this page, right, which are all powered by independent microservices, they can be eventually consistent. In other words, they can be cached, right? Item details do not change every second. Prices don't change every second. Offers also don't change every second. Rating reviews also do not change every second. But one exception to this rule is inventory, right? An item available at this moment can be unavailable the next moment, right? So it is super important that whenever we build an inventory platform, that we always represent the most recent and most accurate inventory, because what the platform is doing here is giving a promise, right? It is giving a promise that this particular item is available for pickup in a store 2 hours from now, or this item can be shipped to your address 1 day from now, right? So those promises are made based on the most accurate information on the inventory, right? Another complexity which is not very apparent here, which is probably unique to Target, is unlike traditional e-commerce retailers, right, where your online orders are fulfilled using large fulfillment centers, the fulfillment centers where they do pick, pack, and shipping, 95% of Target's online orders are actually fulfilled using stores. Your stores are spread across the US, and they all double down as mini fulfillment centers, right? So what that means for our inventory platform is, earlier, when you had to track inventory of all these items across, say, only 10 or 15 fulfillment centers, now you need to do that across 2,000 plus stores, right? The complexity or the dimension of the complexity suddenly just exploded from, say, 10 to 10, 15 volume to over 2,000 times, right? So that's, so if you put all of this together, right, the inventory data that you see here, right, is the microservice that powers this information is powered through a platform that listens to changes to tracks inventory across 2,000 plus stores at a real-time basis, right? So with this background, right, I'm going to just quickly look at the platform characteristics that we have, right? So we have a catalog of over 4 million, and that catalog is present in over 2,000 stores, right? If you do the simple multiplication, that's like billions of item locations at play. We get over 5,000 requests for inventory changes every second. And like I talked about, right, like the 10 millisecond is the accepted latency or the accepted response time that we are trying to solve here, right? One thing that's not probably very apparent is zero P1, P2 incidents, right? If inventory platform is down, Target.com is down, right? And if Target.com is down for 10 minutes, that's like hundreds of thousands of dollars of opportunity cost, right? So Tom earlier talked about the fallacies of distributed computing, right? So one thing I can tell is, right, in any distributed system, everything fails all the time. So what is more important is, right, you build a system that is fault tolerant and resilient and kind of can handle failures under the hood in a way that it doesn't not very apparent to the customer, right? So that's the part about zero P1, P2 incident, right? So with all this put together, we identified 5 design goals for our platform, right? Number one is our data needs to be atomically consistent. What do I mean by that? If there are concurrent requests on the same inventory object, I want to make sure that the data guarantee is there, or the transactions are committed in an atomic way, right? Second thing is, I talked about 10 milliseconds, low latency, read and workload. These are mission critical, right? We talked about high availability. I want to spend a quick second on elasticity, right? So retail is a pretty seasonal business, right? So the kind of traffic that you would see in retail, say on a Black Friday, which is like the rough equivalent of, say, a Diwali, right? Is probably 4 to 5 times higher than a traffic that you would see on a say of February, third week of February or so, right? So auto scaling, right, is a given in every component that we build, right? So every layer that you build has to be auto scalable. Otherwise, you're going to waste tons of servers of money, over provisioning the servers, or you're going to end up under provisioning the server. So we got these 5 goals, and we started going about an objective of kind of how do we meet a response time of 10 milliseconds under 1 million requests per second, right? So the next few slides, I'm going to just talk through the journey of how our architecture evolved through multiple versions and eventually got to where we wanted to be, right? So the first version of the architecture, we started off with a NoSQL and a cache, right? This is a very natural choice for a lot of us. So on the left side, what you see is like you have these thousands of events coming, change events or inventory changes coming from 2,000 plus stores, fulfillment centers. They're all ingested into Cassandra, right? So they are all what I call supply signals, right? And on the right-hand side, you have the demand signal. Demand is nothing but your online orders that you're actually placing in your native web, native apps, or your target.com, right? So in very short, right, supply minus demand is your inventory available. And that data is kind of cached in a object cache. So you're using Cassandra for all the write workloads, and you're using an object cache for all the read workloads, right? So the option looked great on paper. So when we kind of put it to production, the write scaled brilliantly. I think Cassandra's a database that we were intimately familiar with. We've taken it multiple times to production. So no surprises here. The write scaled very, very well. But we had 3 challenges with this approach, right? The one was the data was not immediately consistent, right? So what I mean by that is, let's say I'm building a booking platform for a IPL match, right? So you have a stadium and there is a stand in the stadium which has, say, 500 tickets, right? Now, when you open it up for booking, you're going to see lakhs of requests coming into play almost concurrently, but you cannot sell even a ticket more than 500, right? So the data has to be immediately consistent and not eventually consistent. Otherwise, you're going to end up overselling more seats than you eventually you end up having, right? The second aspect that we had is, right, the rate of change that you see here on the supply side was so high that our read cache was getting invalidated almost every single second, right? So it kind of resulting in a lot of cache miss, and almost at a point question the very purpose of why you need even a read cache, right? So the downside of both these options was our latency or response time were more around, say, 150 to 200 milliseconds instead of 10 milliseconds, right? So we were almost 10x, more than the response time that we wanted to originally achieve, right? So the MVP did not go well, but a lot of learnings, right? And one important learning took us to a radical shift, right? And that is to move from a disk-based architecture to a memory-based architecture, right? I just want a quick show of hands of how many of you folks have worked on in-memory data grids or any memory-based architectures, right? Wonderful, like handful, right? Awesome. So if you look at one of the reasons we moved from a disk-based architecture to an in-memory data grid is the idea is, can I represent the inventory of the entire company, right? So you're talking about billions of data. Can I represent it in one giant memory grid by pooling RAM from multiple servers, right? So one thing to note here is IMDGs are not in-memory databases, right? So there's a critical difference here, right? In an in-memory database, your database is primarily meant for storage. The application logic that you execute on the data that is stored is in a remote server, right? And that's where grid computation differs, right? In grid computation, the code that you run and the data that you have run on the same box, right? And that's why it is blazingly fast, right? In-memory data grids, is it a solve for every problem in life? Probably not, right? If your latency is not mission critical, I wouldn't recommend in-memory data grids. Or if you don't have a large amount of data to store, again, IMDGs are not a good option, right? But it perfectly fit our bill from both the response time perspective and the amount of data that we need to store, right? So two big other advantages: the IO latencies of memory-based architectures, right, are just way faster than even your fastest SSDs that you can buy on the market, right? So because we are dealing in nanoseconds, right? So the IO latencies are super fast, right? So with this kind of a background, right, I want to just spend a second on zoom in a little bit of how an IMDG topology actually works, right? We have several IMDG options available. There is Hazelcast, there is Apache Ignite, there is Infinispan. I think so you can evaluate your own option. But by and large, a lot of the IMDG topologies have a similar layer, right? On the left side, what you see is a load balancer, right? This is your entry point to the grid. This is your access point to the grid where you're getting a flood of requests. And then in the middle, you have a client cluster, right? Think of the client clusters as a very, very lightweight clusters. We do not have any logic placed in here, right? The very purpose of the client cluster existing is to route the request to the server, right? So the client is partition aware. It knows when you want to run a computation on a piece of data, it knows exactly which server and which partition in the server that data is located. All it is doing is routing that data to the server. And then you have the real servers. So this is your pool of terabytes of data that you want to store as as a grid. And then finally, you have your backing store. Now, why do you need a physical store, right? In-memory data grid, by nature, data is all in memory, right? So if somebody pulls the plug, if your stuff comes down, your data is going to be lost. So it's always a very good option to have a right-behind strategy that whenever you update anything on the grid, you have a background thread to update that data in a persistent store, right? So that if your cluster goes down in a disaster scenario, you can rehydrate it back with latest snapshot, right? So with all this in mind, right, let's try to put this topology to action, right? Let's say that we have an e-commerce site and there is a phone launch happening, right? It's a very new model and a new eagerly awaited phone launch just about to happen, right? When the moment of launch strikes, right, you're going to see tons of customers, on this side, right, all placing orders for that phone, right? All these go to the load balancer and they all get distributed to various clients. But all the clients will route the data to the same server because you're going to buy everybody is buying the same phone. You have only 1,000 phones to sell, but you have, thousands, hundreds of thousands of requests coming in, right? So all the clients is doing is they're going to realize that, okay, this product is 1, 2, 3, 4, and it belongs to say partition number 50 in server number 2, right? So it's going to route all these requests to that partition in that, server, right? So this is where the magic of co-located computing happens, right? The logic of actually locking, latching, and providing serialized access to the inventory object all happens on the server. It does not happen on the client. If it were to happen on the client, you would get nowhere closer to meeting a 10 millisecond response, right? So because if it happens on the client, you'll have to make one round trip first to the server, get the data back, then do all the stuff that you have to do on the client side, and then you have to write it back to the server, right? So multiple round trips will be at play here, which is completely avoided. And so even though you say you submit a lack of requests, all wanting to buy the same phone, you will sell exactly 1,000. The remaining 99,000 will get a decline because you get a serialized access to that object, right? So that's the beauty of this option, which is basically running computation on the server itself where the data is present, right? So this option worked great. We met our latencies, we met our response times. We also met the challenge of immediate consistency, right? But there was one big problem, right? We were using the servers for both the read and the write workloads. In a typical e-commerce site, right? I would say the read to write ratio is almost 6:1, right, or 7:1, right? So what you're seeing is, right, when there are so many requests coming in, a lot of them are read workloads. So the question for us was, right, since the CPU of that particular server is getting heated up and it's on fire, is there a way that we can build a cache in front of the server to take care of the read workloads and protect the CPU of that particular server only to do your transactions or only to do your writes, right? So that's the problem that we wanted to solve, right? So then we moved to the third option called version 3 of the architecture, where we use the same grid, but we activated something called as a near cache. So what is a near cache? Near cache is a local cache that actually sits on the client. It's not a huge cache. It's a smaller cache. It's on the heap. But then you can activate the near cache based on requests per second that you're seeing on the server. So let's say I have a ton of requests coming to my server and my CPU is getting heated up. So if I know that the request per second is crossing a particular threshold, I can programmatically activate the near cache on that client. So the subsequent read workload will hit the client and the server will be used only for doing your transactions, right? So this option, again, worked pretty well. So, this is an example how how it will work, right? So you had the phone launch, you had a ton of transactions all going to different clients, but they all come and hit your server number 2, and server number 2 is getting heated up, right? The other servers are nearly collecting dust. They're not doing much, but server number 2 is heated up, right? So when you program, server number 2 now has a logic inside to activate only for that key client cache, right? So all the reads will happen in this client layer and not on the server layer, right? So that's one big advantage that we had, right? So we solved the problem nearly as much as we want, but we were still not there. The challenge was when the data gets updated on the server, all the clients, the near caches in all the clients invalidate at the same time, right? So you can see this vicious cycle happening, right? A value in the server changes, that invalidates all the clients. Now all the clients wants to fetch the same data, so they're going to come and hit the server one more time, right? So you see this vicious cycle kind of continuously playing, right? So this option clearly reduced our CPU hotspot from how it was in version 2 of the architecture, but nearly didn't get us to where we wanted to be at the end of the day, right? That's where we moved to the final option, which is called where we built our own custom cache. So our team built a custom cache called the native memory allocator, right? Which is very different from a near cache, right? The project is in GitHub. You can go and check it out. So what this one does is it has 3 big differences compared to a near cache. Number one is near caches are on heap, right? So you have a cap on the number of data that you can store. If your heap is say 4 GB, and if you store values beyond 4 or 5 GB, right, you will start running into GC overheads, right? Or GC pauses will start hurting your response times, right? But your NMA or your custom cache that we built is completely off heap. You can store 40, 50 GB of data locally without any overhead or any incurrence of GC pauses that we have, right? The second difference that we had was the way we do invalidation between option 3 and option 4 was very different, right? In option 3, when the server is heated up, the clients, all the clients invalidated almost at the same time, right? That is what we solved in option 4. What we did here is when the server, sees a particular value change, all it does is it posts a message in a topic. I mean, think of this as a Kafka topic, but it's not Kafka topic, right? It's an internal data structure. So it posts a message in the topic, and all the clients that you have on the other side, they're listening to that topic, right? So the clients have a background thread through which they actually pull the data from the topic and update it themselves instead of all kind of flooding the server one more time to get the value, right? So this option finally got us to where we wanted to be, which is basically, right, your clients were independent. They were handling all the read workload. The servers were free, from a CPU perspective. The grids worked well. There was only one drawback though, right? The data accuracy that you will see in the client will be off only by a few seconds. But the beauty about the few seconds is you can programmatically control, right? These are configurable. So if you want your data to be even more accurate, you can fine tune it at the cost of more CPU, right? So this is the approach that we eventually got to, hitting like a 10 milliseconds at a 1 million requests per second, right? So, I mean, one thing that I want to share is that when you kind of do grid computing, it was definitely, I talked about auto scaling. So, one advantage of this approach is, right, when the traffic surges in the architecture, the clients can spin up automatically and they'll be up and running in about 2 minutes, right? Because your caches are all local. So that's the advantage of having, a custom cache as well, right? So this is how we got to it, right? As I want to just wrap up, I want to leave you guys with 3 lessons learned, right? I mean, building these kind of architectures take years, right? It will be naive for us to say that, yes, we got it right the first time. It takes us years and years of lessons learned. But if I have to leave you guys with 3 lessons learned from operating an in-memory data grid, I think the number one would be serialization, right? Serialization is a very, very important choice in any grid-based application, right? When your data isn't stored in JSON, right? And memory is not cheap, it's expensive. So you can't store terabytes of data that you have in your grid, right? So what is more important for you is to, do benchmarking of multiple serialization formats. We evaluated protobufs, flat buffers, Javalution, and I'm sure there are a few more. And we, finally figure out which one kind of gives you the best compression rate, right? I mean, if you have 2 terabytes of data in a JSON format, if you serialize it with the right, right format, you can almost bring the size down by anywhere between 5 to 6 times or 6 to 8 times, right? So it's a huge benefit, in serializing this, right? The second thing that I want to talk to you guys about is auto throttling based on real-time TPS. We talked about servers getting heated up because of read workload. But what if your writes were itself so fast, right? What if your writes were getting so flooded that it was causing a huge spike in the CPU? That time you're against a wall, right? The only way for you to prevent the server from falling down is to probably do some kind of back pressure or rate limiting, right? So what we used to do is we had a throughput monitor, which will monitor, the rate at which every write and read traffic is happening for a particular key. If that number breaches a threshold, it will automatically start, sending a HTTP status 429, which is like, rate limiting, right? So that you can throttle that traffic hitting your server. The last thing where I talked about is off-heap versus on-heap. I think, as a programmer, as a developer, right, I love doing stuff on on-heap because on building on-heap caches, it just, you can light it up in a day's time. But when your cache size is over 4 GB or 5 GB, I would strongly recommend for you to consider moving to an off-heap storage, right? When you move to an off-heap storage, you can have a cache easily worth over, 50, 60 GB without any, I would say garbage collection overheads, right? On-heap caches, we've tried multiple garbage collector policy, G1, GC, or like ZGC. They still have some level of overhead that you can avoid beyond 4 GB or 5 GB, right? So with that, I want to just wrap up this session. It was the idea here is to share our learnings in building a distributed, architectures to this larger group, right? So I'll be here if you guys have any questions. But I want to thank you guys again for listening and have a wonderful rest of the day.